Emily and Jerry are studying generators and alternators. So this picture here, although it looks like a motor, in this case we're rotating it by hand, which means it works as a generator. So this is a generator. Generators are DC, alternators are AC. The question is, they tested the device by connecting it to an oscilloscope and rotating the coil. This figure 4 shows the graphs of magnetic flux. And the voltage for each one. So here's the voltage and here's the flux, and you have to choose the right one. So which one is the correct voltage? Now if you look at all of them, the dotted lines are the same in every case. So the flux starts out very high, there's lots of flux, the field lines go through here, lots of field lines going through it. As this loop rotates, and rotates like that, that goes down to zero. Field lines go through that area, so that's zero flux, and that's why the flux goes from very high to zero. The loop flips over and you get the negative because the loop's facing the other way, and then the loop goes back through that point where it's at 90 degrees, so there's zero flux, and then it goes back to full flux again. But what does the voltage look like? Comparing the voltage and the flux is through Faraday's law. And that looks like the EMF equals N change in flux, negative N, change in flux over change in time. And what this part here means, the change in flux over the change in time, is the gradient of a flux time graph. So it's the gradient of this dotted thing here. So let's talk about the gradient of this guy. We'll draw another graph over here. Alright, at the start, the gradient is very flat, so the gradient is 0 here. The gradient here is very, very steep, and this gradient is negative, but because of the value, the negative value here, negative times a negative, so the gradient here is positive at this point. Down here, as it flattens out, the gradient here again, as it goes from steep, just as it goes through here, it goes through 0. And the gradient here is very steep, and it's a positive gradient because it's getting bigger, but because of the negative we say it's now become negative, and then up here again the gradient goes to 0. So we're looking for a graph that at the first point is at 0. Let's do it in red. Is at 0, then is positive, then is 0, then is negative, then is 0. So which graph of the voltage looks like that? And the answer is A. Alright. Next one, explain the difference between and function between split ring commutator and slip rings. That sounds very similar, slip rings and split ring commutator, but they're two different things. And when they're used in generating electricity, the slip rings are used for AC and the split ring commutator is used for DC. Describe situations in which these two are used. So we'll start off with the slip rings. So what I want to describe for each of these is I want to say how they work, and then I'm going to say what voltage they give out. So is that AC or is it DC? So how they work. Slip rings they do is they maintain contact with the same external connection. So slip rings maintain contact with the same external connection. Now if you don't really know what that means, you need to go back and have a look at pictures in your notes of slip rings and see, as the thing rotates around, it's always going to be touching the same output connection. And this gives an AC voltage. We can draw a little graph voltage. And then we've got the split ring commutator. And the split ring commutator, it changes connection to output, or external we'll call it, contacts every half cycle. It does the opposite of what it does in a motor, where it flips the current every half cycle. This time it changes the connection to the external contacts every half cycle. And what does this do? It gives DC voltage. Again, you need to go and have a look at a diagram of commutators to see, as you rotate a generator by hand, if it has a commutator, it changes the connection to the external contacts every half cycle. And the voltage looks like, we call this pulse DC, if you ever want to use a really sexy physics term, pulse DC.